Okay. So when we talk about paleogeography, we're talking about the study of historical geography of the earth. So how was the earth before and how does it relate to the present? All right, please follow. I'm going to give you guys the notes. There's no point copying exactly what's on the note, but I'm not saying don't take notes. I'm saying take notes that you think you can find on the slide. And the way I usually do it, if this is slide 1 or 2, I don't know what the number of slides is, but you probably just maybe take the title or take the number and then maybe jot some things that you think are not on the slide. But most importantly, don't copy verbatim what you see on the screen, because at the end of the day, you're going to get it, right? So what the point is, just wasting time. Why not listen and get the full understanding and explanation of the concept, and then we'll drive with that, okay? All right. So, when we talk about the study of historical geography, what we're saying is how physical features such as the continents, mountains, and oceans were arranged in the past. How does that relate to the present? How did we get to where we are right now with these continents? All right? The objective for understanding the historical geography of the earth is for us to reconstruct past positions of the continents and oceans. Not only that, understand the fundamental concept of plate tectonics, which is continental drift. Alright? And last but not least, study the impact of geography on our past climates and life. Do you understand how all of this now fits in? Paloegeography, study of the past geography of the earth. All right, understanding how all of these mountains, continents were in the past and how they came to be now, right? And then understanding this will help us understand some fundamental concepts such as continental drifts, okay, climates, and life. Are we on the same page?
Yes, sir.
Are we on the same page?
Yes, sir.
All right. Are you with us?
No, sir.
Go, sir. Are you? Okay. Now, this is sort of the objective for studying the historic past. Not the objective for today, but the objective for studying why we study the. And again, you're going to see the importance of paleogeography. What are the tools we use to understand ancient geography of the earth? We talk about fossil distribution, as we're going to see when I begin to explain it. Stratigraphy, most importantly, the plate tectonics concepts, all right? And then we talk about paleomagnetism, which on its own we're going to study, right, before the end of the lecture, and then sedimentology. These are the tools we need and methods we need to understand, the ancient geography. And then the key concept about this is that before, in the past, we had, a supercontinent, right, called Pangaea, all right? And to the north, we had Laurasia. To the south, we have Gondwana, all right? That's the main concept behind it, all right? We started off with a supercontinent that began to drift over time to the present position. That's the main concept about the past geography as it relates to the present. And then you can't talk about the breakup of Pangaea into the present continent without talking about continental drift. And that was why I said earlier that this is a fundamental concept in understanding ancient geography of the earth. So put up your phones, put it in your pocket, put it on silent and put it off, or put it out of sight, okay? And most importantly, I'm going to show you maps of how the relationship between this distribution of continents and oceans over time, right? Essentially, that's why we're talking about past positions of the continents relative to what it is right now. Who is this young man studying us with all of this ancient sound? All right. So, what is the theory of plate tectonics essentially? It was proposed when in the mid-20th century, precisely we're talking about the 1990s basically, all right? So 1950s, thereabout, all right? And then what is essentially that it shows that the Earth basically is made up of large numbers of diverse, unrelated geologic facts that are interrelated. And the theory was the linkage to two ideas, to two basic ideas, the first one being continental drift and the second one being seafloor spreading. With those two ideas, right, we're able to come up with the theory of continental drift. And that theory simply states that the Earth is made up of lithospheric plates that are moving or constantly in motion, right, and have moved since over the last 200 million years. All right? So it involves a number of large plates, numerous small plates composed of crust and upper mantle. The crust and the upper mantle makes up the lithosphere, all right? And they move slowly, change their size as well as their shape as they do that. Okay? So essentially, the Earth is not static. It's not static, and if it's not static, it means that it is dynamic. The Earth's surface is dynamic because you've got about 7 large plates and several smaller plates that are in constant motion, and as they do that, they change their shape as well as their sizes. Are we on the same thing?
Yes, sir.
All right. And you can stop me anytime to ask questions. All right? You can stop me at any time to ask questions. Talk to me.
In the previous slide, you said the Earth was mostly contained on like supercontinent called Pangaea.
Yeah.
Like you talked about Pangaea, but there was also other ones in that slide. Those
Laurasia
yeah.
to the north and Gondwana to the south.
I don't understand what those are.
Pangaea is the supercontinent. I'm going to show you as we drive. But have you at the back of the mind that we started off with what we call Pangaea. And as time went on, we got into 2 subcontinents, Laurasia to the north, Gondwana to the land. And as time went on, we're talking about breakage of the supercontinent Pangaea now, right? And all of those Laurasia and Gondwana land began to separate again into what we have today. To the south, we had South America, we had Africa, we had, do you get what I mean now?
Yes, yes.
Australia, and to the north, we had all of that, right? We're going to get there. But know that we started off with Pangaea. All right?
Yes.
Okay. Now, the data behind studying all of this, right, was essentially collected, right, after World War II. And that provided the scientific breakthrough for understanding plate tectonics. All right? And that sort of data is called geophysical data. All right? So you got echo sounding from the sea floor, all right? Understanding what the sea floor was all about. All right? Because before now, it was thought that the sea floor was dead and inactive. But with geophysical data, echo sounding, understanding of the makeup of the seafloor, we now understood that the seafloor was in fact active and that it had what we call mid-oceanic ridges and deep trenches. We also had earthquakes and volcanics that are associated with these mid-oceanic ridges. All right. The other kind of data we had were, magnetic field data. All right, that made us understand some critical concepts that I'm also going to explain as we go on. All right, and in fact, we had a global network of seismometers that provided information on earthquake patterns. Remember, the plate tectonic theory was, in fact, talked about first by a guy called Alfred Wegener in 1912. It proposed some lines of evidences that, to back up his theory of plate tectonics. I'm going to talk about it as we try, right? But unfortunately, his theory was rejected because he couldn't provide the driving forces for why plates would drift. Alright? So the theory was initially rejected. And then after World War II, and that was what I was talking about, we began to develop some geophysical tools that in fact provided more proof for the fact that continents actually drifted. And that was when the theory was finally accepted around 1960. Are we still together?
Yes, sir.
Alright, are we following this?
Yes, sir.
Please follow. Alright, so we talked about magnetometers, talked about seismometers, right? As well as echo-sounding. Echo-sounding for the seafloor, magnetometers for to discover the Earth's magnetic field, and then seismometers to begin to talk about earthquake patterns. Now, this is our original here. Alright? He was the first guy to propose the theory of continental drift. Alright? And then, in fact, he said that for the first time that drift was still taking place and had been since the last 200 million years. Alright? He supported these ideas with some lines of evidences, right, that drift had taken place, and Taylor, another guy, proposed that in fact, mountain belts formed at the leading edges of drifting continents, such as you can see here. So, if you look at these arrows, right, they tell you where the plates are moving towards, and it was saying that where plates converge, we had mountain belts. Alright? This is Pangaea. Alright? And Wagner proposed that at that time we had a single supercontinent called Pangaea. Alright? And the rest of the sea, so if you flip this, right, we had Patalasa, which was the sea there. Alright? And all of a sudden, since then, you can see Pangaea, we said to the north we had Laurasia, right? Yeah. And to the south we had Gondwana. And that was about 200 million years ago. And as we began to come through time, around 135 million years, we could see that these plates began to separate. So we went through 65 million years, and you can see North America, right, which is part of now Laurasia, right, Europe and Asia breaking up, Laurasia here. And then to the south, where we had Gondwana, we had South America, Africa, India, Antarctica, and Australia. Are we still together?
Yes, sir.
Are we following this?
Yes, sir.
All right. And then up to the present day, which is 0 now, million years, you can see that this looks like the world map, isn't it? And we're saying we started off with Pangaea as a supercontinent, and over time, we now have this. So you can in fact see that, it's like a jigsaw puzzle, right? Where we can fit everything together through time. And that's what we're talking about, the study of ancient geography of the earth. Are we on the same page?
Yeah.
Alright. We're briefly going to talk about the science or the evidences put together to arrive at that final map, right? So the science behind how we started off with Pangaea and how we broke up to where we are today. So we're just going to name some lines of evidences, and that will be it for paleogeography. Okay? Good. What is the first line of evidence? All right, the evidence to support the theory of plate tectonics. So the shape of the coastline. So if you look at the coastline, you can see that it fits like a jigsaw puzzle, right? And that was a strong evidence that, in fact, these continents were once together and they drifted to their present position. That was the first evidence. But what was the mechanism? We didn't know at that time. So this was from Paloegeography. All right, the coastline fit. He went on to begin to talk about paleoclimatic evidence, all right? And if you look at this, right, ancient climatic zones match up when continents are moved back to their present position. So if you started off with what we had, Pangaea, the Tethys Sea, right? So let's say immediately after breakup, you can see to the south. So as you move towards the pole, what do you get? It gets increasingly cold, right? So you move from temperate regions to polar regions, right? So polar regions are characterized by ice, all right? So what we had was glaciers, basically. You can see how all of these places have glacier, right?
Yes, sir.
Present day, you can see that these continents had drifted to their present position, but they still had remnants of evidence that they were once together. So, at this location, you can see some glaciers, you can see some glossopterid fossils. I don't want to talk about those fossils right now. You can see so let's stick with glaciers, right? You can see remnants all over the place, which suggested that, in fact, if you piece all of this back, right, they fitted together. And the fact that they have drifted and still retain some remnants of those glacier deposits suggests that they were once together in that part. Are we still together?
Yes, sir.
Good. Alright? And then number 3, we had fossil evidence, which implies once continuous land connection between now separated areas. So the major fossil in this case, on here you can see several fossils, okay? But the story behind, the major story behind this fossil evidence was this fossil here called Mesosaurus, the fossil of this freshwater reptile here. Alright? And the idea behind it is that Mesosaurus cannot have swum, right, between South America and South Africa. Do you understand?
Yeah.
That it doesn't have that capacity to swim that distance. And the fact that you can find it at this location and this location should suggest that the continents were once together. Alright? Very important, Mesosaurus. Alright? So this is fossil evidence. Alright? We find it in the present day at these 2 locations, which suggest that in time past, those continents were once together. And then we have again fossil evidence, Glossopteris. Okay? It's a plant fossil, and this is what it looks like. You can see that it's represented in green here. Alright? You can see in time past, this was the location, spanning through all of these continents. But today, you can find remnants of it all over the place here. So fossil evidence, flora, Mesosaurus as an example. Fossil evidence, fauna, Glossopteris as an example. Are we still together?
Yes, sir.
Don't slip off on me. Is it a boring class?
No, sir.
Are you sure?
Yes,
But I
sir.
can see some people sleeping. Some people they sleep at night. Alright. Number 4 evidence. We're going to skip this because it still falls under some sort of fossil present day organisms and all of that. Alright, we're just going to skip this. And then let's stay with this for a bit. Number 5. Right? You can see geologic similarities between South America, Africa, and India. We know that because we can, when we do a correlation, we can see some stratigraphic correlation between rock layers that span through all of these countries. Okay? We can see mountain belts, right, and geologic structures, right, that span through all of these countries. Not only that, we can also see basement rocks, okay, that are similar in Gabon and in Brazil. And I'm going to show you, let's start from here, right, where we have correlation of rocks. You can see that you have Argentina, Brazil, Falkland Island, down to Tasmania, right? You can see coal beds can be correlated across. You can also see sea lights. You can see Glossopteris correlated across. That suggests that, these continents were once together. So this is geological evidence, right? The other thing is, you can see mountains, right? Younger and that formed earlier, as well as older mountains, can also be correlated across these continents. All right. For instance, the Caledonia Mountain, you can see it in Europe, okay, and in North America. The Appalachian Mountain, you can also see it across this boundary. All right. Are we see together?
Yes, sir.
You can also see the younger mountains, okay, span through all of these continents. And there are still remnants of those mountains in the present day location. And those are strong evidences for suggesting that, in fact, these continents were once together in time past. And last but not least, we had igneous provinces. Okay, you can see Precambrian Notocyte. Okay, you can see Mesozoic dolerite. Across these boundaries, which suggest that they were once together. So those were strong evidences, and all of those evidences were suggested by Paloegeography. But remember, I said something earlier that his theory was rejected. It was rejected because he didn't provide the driving force. In fact, he suggested a theory and he started looking for evidences to back up his theory. And that is not the scientific way for proposing a theory. First off, we have the evidences, and then based on that, we propose a theory. But we propose a theory first, and then start looking for evidences to back up his theory. We're talking about the reasons why his theory was rejected. And then, all of a sudden, with more information, all right, like I told you, echo sounding was used to discover that the seabed was what? Active. The seabed was active. And from there, we knew that there was a rift valley of East Africa, which indicates a continental breakup. He said the seabed was thought of as being inactive. But with the discovery of the activities on the seabed and the discovery of a rift valley, which suggested that the continents actually drifted. Alright? We talked about similarities already, so I didn't want to talk about our point anymore. And then there's evidence of subsidence in the oceans. And that pertains to, a guy called Wilson Tussell, who discovered hotspots. What are hotspots? Hotspots are, the places where you have stationary plumes that basically try to whirl and form, a volcano on the surface. Now, what he discovered, Wilson Tussell, what he discovered was that, in fact, they were what we call guyons, and these are flat-topped seamounts. They emanate from this volcanic chain of islands. Now, how do you get volcanic chain of islands? Look at the screen. You start off. So imagine, right, that if this was a stationary lithosphere, right, and you have upwelling of magma here, on the surface, what are you going to discover? You're going to discover a volcanic island or a volcano, right?
Yes, sir.
Now, if the continent was stationary through time, we're just going to have a single volcano, right? A single volcano just above this hot spot, right?
Yes, sir.
But because the continent, right, was in constant drifting mode, all right, what will happen? Say, for instance, the continent started drifting to my right. This volcano here is going to become extinct. What does that mean? Inactive, right? And then what will happen here on this surface? A new volcano, right? And it's going to remain there for some time, and then with continuous drift, you're just going to have a chain of volcanoes on the surface, with the previous one beginning to become extinct, more older and extinct as time went by. Now, if this is underwater, for instance, you're going to have the erosion of those previous ones underwater, and that's what will give you this flat-top seamount. It's going to be eroded because you're going to have waves walking on working on the volcano, right? And then it's going to be flat topped. But when you now have the active plume working, you're going to have an active volcano more than one. Does that make sense? And that's what this diagram is talking about. So you can see the drift of this oceanic lithosphere. You can see the present day active volcano. You can see that all of a sudden you are beginning to erode this pre-existing one, right? And you end up with a coil, a flat top seamount on here. And that's what explains this evidence here. Yeah. Are we on the same page?
Yes, sir.
All right. How are we doing for time? All right. And last one on the list, we had the is it the last one? No, not the last one. We had the discovery of the mid-oceanic ridges, which are sites of seafloor spreading. And alongside that, at mid-oceanic ridges, we have some interesting characteristics. For instance, there was high heat flows. And that high heat flow suggests that, we had, the eruption of magma at the surface, right? And if you look at the heat flow data, when we get to the mid-oceanic ridge, we have high heat flow, but away from there we have, in fact, almost zero farther away. All right? And then we had, we talked about Rift Valley, all right? What was also important was consistently these spreading centers were volcanoes and earthquakes. So if you look at this map, this is North America, this is Africa here, right? This is the South America down here. And you can see all along here, this is a divergent margin, all right? A spreading center. You can see the Rift Valley, okay? The Mid-Atlantic Ridge, and all of these small dots tells us that these spreading centers are consistent with earthquakes and volcanoes. Are we on the same page?
Yes, sir.
All right, we're talking about evidences to prove that, in fact, this continent is drifted over time. All right? And last but not least, there was the paleomagnetism evidence that we're now going to go on to now to further, nail not this aspect, but because we need to talk about it, then we need to talk about it. All right? How does the paleomagnetism evidence work? We're going to talk about it in the next slide. But know that it was an evidence that further backed up, all right, the theory of continental drift. All right? So add with all of, so including the previous one I talked about, seafloor spreading, so mid-oceanic ridge, seafloor spreading and all of this, and paleomagnetism. These were now the new evidences, not by Paloegeography anymore, right? But by some other guys. For instance, Wilson Tucson, seafloor spreading was by, and you don't need to know these things because I won't ask you questions about it. Seafloor spreading was by a guy called Hess, all right? And then paleomagnetism was by some guys from the US called Hyben and Luca. All right. I don't say are you guys following this? If you're not following, just show by ways of hand, try ask questions. Because there's no point sitting in here, you're not following, and you're just then in the exam, remember you're going to walk alone. Alright? So if you don't know, ask questions now. This is the time to ask questions. Yes, talk to me. Yeah. They were active before. Well, so for instance, an active volcano, right, will become inactive because plates have drifted. So you now have the development of a new active volcano where you have a stationary plume. So the driver for all of this is the stationary plume that is causing the volcano to be active. But because plates are in constant motion, right, you're going to have the development of a new one, but this previous active one will now become extinct and with time become a coiled. Period is what? The flat top. Sima. Alright. Are we on the same page? Do you understand now? Okay. Now let's begin to talk about this on to the next one. So what is it? So this is a map of the plate tectonics, major tectonic plates. There are about 7 of them, including North America, South America, right? That is 2, right? 1, 2, right? 3, right? 4, right? Are we still together?
Yes.
5, the 6, 7. 7 major ones. Alright? But we have other smaller ones, including Nazca. Alright? The Caribbean plate. There's one called Coscos plate, but it's not shown here. Scotia plate is a Coscos. Alright? This Juan de Fuca plate. Alright? And then where's the Philippine plate? Where's it? Right. These are the smaller plates, okay? There are about half a dozen. Okay, are we on the same page now?
Yes, sir.
Alright. What is the importance of all of this? With these, with understanding the past geography, we can explain past climatic zones. I showed you, right? Where we had glaciers that were once together, now they have drifted, right? So we can understand that. We can also talk about, fossil fuels and mineral resources. For instance, coal we develop in temperate regions, right?
Yes.
You can explore for coal. You can explore for mineral resources because we know the conditions in which they were formed. And then we can begin to talk about biological evolution and extinction events. For instance, we talked about some fossils, right? We talked about Glossopteris, we talked about Mesosaurus. Alright? So putting all of this together, it can help us understand some of all of these important issues. So that's all about paleogeography. In the next